Good afternoon in Poland, good morning in US, or wherever you are. So thanks for visiting us at this seminar. The seminar will be delivered by a pair of authors in the order Wojciech Słomczyński first and later Anna Szymusiak. I hope we'll learn more what means the magic word morphophoric. So the title is, as you see, Morphophoric measurements in generalized probabilistic theories. So, Wojciech and Anna, please, the screen is yours.
Indeed, the title of our talk is somewhat exotic, Morphophoric measurements in generalized probabilistic theories. So I would like to start from saying what is our aim. And our aim is to generalized cubism approach techniques and to see how much Q is in cubism. So to transfer this approach to some more general setting. So what is this more general setting? Generalized probabilistic theories are, in a sense, generalization of quantum mechanics and classical mechanics and much more. There are different definitions and different approaches to generalized probabilistic theories. So I would like just not to introduce notion in formal way, but to explain what are ingredients of the theories. We have some vector space, real vector space, which is an order vector space. Namely, there is some closed proper generating cone inside, which induces the order. There is also some element of some functional E, the unit, and the states are the set of states is the set of all positive elements such that the unit on these elements is 1. And this set, say B, is a base of this cone, of these positive cones. There are also some elements, some extreme boundary of the set, and they can be interpreted as pure states. So we have, at the end, we obtain some Banach space called base norm space, and some dual Banach space called order unit space. And the elements of this dual space, which lies between 0 and E, are called effects. We assume then that no restriction hypothesis, so all this say simple observables or tests can be realized physically. And an effect on the state is just the probability that this effect holds. So this quite old stuff, it started, I think, in early 70s under a different name, statistical or operational approach to physical theories. And it is due some mathematicians like Martin Edwards, Edward Davis, and John Lewis, and their results are based on other results of British School of Functional Analysis, namely Alan Ellis and David Edwards, on order vector spaces. From the beginning of 21st century, there is some renewal of this theory now rather in the finite dimensional setting and under different name, generalized probabilistic theories. It is a huge wealth, these theories, but we will concentrate on a subset of these theories, namely so-called strongly dual Gpts. This assumption of strong duality is very crucial assumption. I will explain this later, but on the other hand, it is not very restrictive. There's still plenty of strongly dual generalized probabilistic theories. What is the definition? We assume that there is some map T, isomorphic map between order isomorphic between this space V and the dual space V star, and such that the bilinear form given by T on V on W is an inner product. So in this strong dual generalized probability theories, we can introduce some geometry on the set of states, namely some inner product structure. There is plenty of papers on the strongly dual GPTs. There are some equivalent conditions, some sufficient conditions, namely this strong duality can be obtained from some assumptions on symmetry of pure states or other assumptions. Now I would like to give you some examples of these strongly dual GPTs, and I think two of them are the most important. The first is classical state space, and here we have Euclidean space with natural positive cone, and the space of states is just standard probability simplex. So states are here just finite probabilities. Of course, we have a discrete set of pure states here. They are the vertices of this standard simplex. The inner product is just natural inner product in RD. And also the set of effects has natural interpretation. The other completely different example is probably best known is quantum state space, where this real vector space is the space of Hermitian matrices, and positive cone is the set of positive semi-defined Hermitian matrices. The unit is just trace operator, and the states are just density matrices, and of course pure states can be interpreted as one-dimensional projections or as projective complex space. And again, there is a natural inner product here, Hilbert-Schmidt product, and normal definition of effects. But there are some other interesting examples. For instance, in R3, there is a pentagonal space. It could be a pentagon, but it can be also some other regular polytope with odd number of vertices, and we have to put this pentagon in a special way in this three-dimensional space to obtain a strongly dual GPT here. There is also a huge class of famous Gpts that are generated by Jordan algebras. Here, the space is a finite dimensional Jordan algebra. The positive cone is given by the squares of elements of this space, because there is a linear operation, additional linear operation in a Jordan algebra. And in this class, there are some quantum-like systems over reals, quaternions, octonions in dimension 3, and also balls, just balls as a state spaces. And under some additional axioms, we can assume that a GPT is in this class of Jordan algebra generated GPTs. So there is plenty of examples, and we try to look at their common features. In every such space, we have something which can be called maximally mixed state. This state lies, in a sense, in the middle of this of B, of the state space, and is orthogonal to B, or in other words, this M is an orthogonal projection of 0 on B. What is important here, we have two numbers. The first one we called epsilon, and there is a squared distance of this maximally mixed states from 0, and the other one is called chi, and is the maximal distance of a state from 0. One can prove that such maximal state is necessarily a pure state, and this gives us some kind of geometry of this state space. With the help of this maximal mixed state, we can define something which works as a we can call it block representation of states. It is just W minus this maximally mixed state, and they are elements of not on of an affine space as states, but elements of vector space, and V0, and the dimension of the space is dimension of the state of the space V minus 1. Okay. To say more about the geometry of the state space, we have to define two notions. The first one is a polar state, but this is a polar operation in an affine subspace of B, with the center at some point C and of some radius S, or it is a polar with respect to some ball. Taking the inversion operation on this polar, we obtain dual set to A, which is probably most easily described by such set of of inequalities. With this operation, one can prove that the state space is necessarily self-dual, and this is a result of this self-duality introduced, of the self-duality assumption which we made at the beginning. We can also obtain some other elements of cubism, like fundamental inequalities, which are for block vectors, and finally one can prove that this state of space lies somewhere between two balls, larger and smaller, and we can calculate the radiuses of this balls, and here this expression chi over epsilon is present. Also, we can prove that the angle between block vectors cannot be too large. There is a limit here, and in this also this parameter is present in this inequality. So it seems that this parameter is important for understanding geometry of state space in this setting. So I would like to say you something more about this parameter. I don't know the interpretation of this parameter in general case, but under the assumption of spectrality, which means that some of the spaces are spectral, some are not. For instance, Pentagon is not, but all these Jordan algebras.
Be so kind as to remind us what the spectrality means.
Yes, in a minute. The spectrality means that the state, each state can be decomposed into the sum of orthogonal states. Orthogonal because we have a scalar product, inner product in this space. So we can say about orthogonal states. And spectrality means that each state can be decomposed into the sum of orthogonal space, like in quantum mechanics or in classical mechanics. And under this assumption, this parameter is just the maximal cardinality of ensemble of orthogonal vectors, which is balanced, which means that the mean value of this orthogonal vectors is just a maximally mixed space. And we can call this an orthogonal frame. For classical mechanics, for classical probability theory, it's just the dimension of the space. In quantum mechanics, the dimension of the space is real dimension is d squared, but this capacity is just d. It's because it's the maximal number of the orthogonal vectors. For Pentagon, it is this parameter is equal to the square root of 5. So definitely it cannot be it means that this Pentagon space is not spectral, because this must be natural number otherwise. But it seems that this parameter is crucial, and in a sense because all these notions depend on this underlying map T between the space and the dual space. And of course, we can multiply this map T by some lambda, and those two parameters depends on this lambda, but not chi over epsilon. And the second part of the title of our talk, it is morphophoric measurement. This a class of measurements, a huge class of measurements, which we identified, namely Anna did, as a counterpart of SIC-POVM measurement in the cubism. What is morphophoric measurement? The measurement is just a collection of effects such that the sum of these effects is equal to this unit. Measurement or observable. And morphophoric measurement is measurement which is just a similarity between this between the state space and its image, and we can define this in three equivalent ways, and it is why we need this self-duality, because we would like to define morphophoric measurement in such a way that the geometry of the state space and geometry of its image, and its image lies somewhere in probability simplex, is basically the same. We can call this image Gplex, because it's in a sense generalized Qplex and generalized simplex. Morphophoric measurements are necessarily informationally complete, so they are one-to-one. We can reproduce the state knowing the results of the measurement. And here we have such a simple criterion for morphophoricity. Morphophoric means that it's morphophoros from Greek, that it's the shapes of the objects in B and in this image are just the same. The geometry, the internal geometry of these two sets, B and pi on B, is just the same, but the external geometry is in a sense different, because they lies in different space. B lies in this space B, and this Gplex lies somewhere inside the classical simplex. So for spectral general probability theories, P is morphophoric if it sends these orthogonal frames into equiangular lines. And I think that it is almost time for Anya, but I would like to present the last two slides of my talk. If we have two measurements, which is in a sense a crucial point, I think, in cubism. One is the measurement, which in cubism is just SIC-POVM, and we have to have an instrument that is the rule which describes us the states of the system after the measurement, and we can define it with the help of such maps from state space to positive cones, where the observable is given by the norms of these maps, and the state after the measurement is just given by this expression. It is in the sense generalization of known leaders from Neumann measurement in quantum mechanics, but it's a very general scheme. It's probably the most general scheme of describing the instruments, measurement instruments possible. So we have an instrument and we have another measurement. And that we have some mild assumption about this instrument, which is not very restrictive anyway. Then we have an equation which links the results of this basic measurement called in cubism the measurement in the sky with the results of this measurement with the second measurement on the ground. Of course, it is not very similar to the bias equation in this form, but what is surprising for SIC-POVMs and for cubism, those two equations are just equivalent, and in many other cases one can write this equation in this bias-like form, not in every case, but in some cases for some instruments and for some morphophoric measurements. All these terms here in this equation can be interpreted in the probability language, and you see here is again this parameter chi over epsilon, and here is this similarity constant alpha. So we obtain in this way a sort of generalization of primal equation or Gleichung. And I think that now it is time for Anya to give us a kind of excursion in the world of morphophoric measurements.
Yes, but Wojtek, maybe let's ask the audience if they have some questions concerning your part now, perhaps, if you agree.
Okay.
So, are there any questions from the audience to Wojciech?
I have a couple of questions. So
yes.
Can you please give an example of where do we find pentagonal space in nature? Or I mean, do we have any physical processes where do we find pentagonal space?
You mean of GPTs or morphophoric measurements?
Of GPT.
It is quantum mechanics is the first example. The classical mechanics is the second example. And there is a lot of toy models in a sense, which are not very, I'm afraid, they have no physical realization, but they are, just toy models, like quantum mechanics over quaternions, which is a subject well known by Carol. I think Carol wrote a paper about this, or quantum mechanics over octonions in dimension 3, and so on. So I think that there are basic two examples: classical mechanics and quantum mechanics, and
several generalizations of quantum theory you might think of.
Yes. So it's, and I think that Anya in few minutes present you a lot of examples of morphophoric measurements.
Thanks. So if there are no further questions, of course you will have a chance to ask.
I have one, Carl, and there's also someone with their hand up. So maybe that person should go first, and then I'd like to follow up on Liliana or something like that.
I'm sorry, I can't see
Yes,
in my
Liliana, yes, I got it. So Liliana, do you have any question right now? Or you want to raise your hand just to cheer up the speaker?
probably
So-
the second.
So Christoph, maybe I'm not in contact with Liliana. Maybe Christopher, could you pose your question?
Yes, so coming back to the toy theories, you mentioned quaternions, but quantum mechanics over the real numbers is
Yes.
another toy theory.
Yes, yes.
Is that an
that's true.
example of a toy theory where there is no morphophoric map?
It's a good question, and a good question, and in fact, I don't know. I thought a few minutes about this question, and I don't know. I don't know. The question is in. I understand that whether it is possible in every GPT to construct a morphophoric measurement, and the answer is I don't know.
Well, in the real
I hope
case,
so. I hope
in
so.
the real case, you cannot get a maximal set of equiangular. You cannot get a set of equiangular lines that is large enough to span the space of operators. So if I understood your result correctly, there's a mapping between, I mean, there's an equivalence between a morphophoric measurement and a measurement that has the equiangular line condition.
But it should not be a maximal set of equiangular lines. Not necessarily.
Not
Because-
necessarily.
Because the number of these equiangular lines is the same as this number of effects in a measurement. So it is not necessarily the maximal number of equiangular lines.
Okay, okay. In
Good.
any case, it's not a trivial question. It's not obvious.
Well, I don't know the answer. Maybe the question is easy, but well, maybe I have to think more about this question. But it's a very crucial question.
Okay,
Okay,
thank you.
thanks, Christopher, for questions, Wojciech for answering. And now I think we can move to the next speaker of this seminar. So Anna, can you continue, take up?
Yeah, sure.
Nice to see you, by the way, and your bike.
Well, I've got some problem here.
So can you share the screen? Please check.
I'm not sharing a screen anymore.
And you have separate files, yes? Separate presentation.
Yes.
Yes, yes, yes.
Is there a problem with sharing your screen or?
Okay.
Yes. Now
Is
we
it
see.
okay? Yes.
Yes, yes.
You
Morphophoric,
can
we can, yes. So possibly you might make it even larger, or
full screen.
Yeah, sure.
it's like, yes, pełny ekran, very well. Great. So please continue. Yes.
Okay, so here's just a reminder what we mean by morphophoric measurement. So it's a measurement that maps the state space to the probability simplex in such a way that the geometry is the same here and here. So it preserves the shape, and that's the meaning of the word morphophoric. First, I would like to tell you something about the equivalent condition for the morphophoricity. And this condition is very simple. And but first, I need to give you a little reminder of the key notion here, which is a tight frame. I guess a lot of you have already heard about it and know well this notion, but just in case there are some people that that are not familiar with these objects, here is a short reminder. So a tight frame is a set of vectors in a Hilbert space such that we've got this Fourier-like series decomposition. So we've got this positive alpha here that and this set of vectors allows us for this Fourier-like decomposition of any vector. So in some sense, we can think of tight frames as a generalization of an orthonormal basis, in the sense that it's very special generalization, because we do not longer require these vectors to be orthogonal, to be normalized, or even to form a basis. I mean, they need to span the whole space, but the cardinality of this set can be obviously larger than the dimension of the Hilbert space. So the generalization is that in this sense that we've got this Fourier-like series, or if you wish, you can also think of this Parseval-like equality. And some most important examples of tight frames are, for example, in two-dimensional real space, we've got the vertices of the regular polygons centered at 0. In n-dimensional real space, we've got the regular n-dimensional simplex, the hypercube, and the cross polytope, which are all also centered at 0. And in d-dimensional complex space, we've got SIC sets under assumption they exist, or the mutually unbiased basis, and they do not have to be necessarily complete. Any set of mutually unbiased bases form a tight frame. So these are some basic examples of tight frames, and why do we need them? Why are we interested in these tight frames in this context of morphophoricity? Well, that's explained here in this theorem, which gives equivalent condition for the measurement to be morphophoric. Namely, if we take the effects from our measurement and map them back by the transformation T to our space V, and then we apply the orthogonal projection onto the space V0. So that was the space where the unit functional E gives us 0. Then this set of vectors is a tight frame in V0 with the frame bound alpha. So alpha was this square of the similarity ratio in the definition of the morphophoricity. And we can also calculate.
Sorry, just a simple question. The theorem is somehow yours or taken from the literature?
No, it's ours.
Great, great. So, and it can be proved, I presume.
Well, it's a theorem, so it has a proof.
Yes, yes. So it is a theorem. Okay, okay. And now, so the bounds. Is it the bound is also new? I mean, this the result here, this for alpha, or the same quantity somehow appeared somewhere in the bounds for SIC-POVMs. No, I mean exactly this formula for expression for alpha.
Well, it's actually it's based on our previous paper which we wrote about the morphophoric POVMs, and this is just a generalization of this result.
Okay, but it's not related somehow to bounds for T designs, for instance. Or you are unsure?
I mean, it can be related, but I think that there's no direct.
Okay. So thank you. Please continue.
Relation. Okay, and some simple observation is that this tight frame is always balanced, which means that these vectors sum up to 0. And obviously, since V is now the Hilbert space, because this map T induced an inner product on this space, then we know that V and the dual space of V are isomorphic. So, so this condition for the morphophoricity can be also equivalently defined by the condition that the projections of the effects of this morphophoric POVM onto the subspace, the dual subspace of V0 is a tight frame and with the same frame bound alpha. So that's just the whichever definition is more convenient for you. And as I said, this condition is very simple in the sense that it is very simple to be checked, to be verified, because, okay, I didn't put it here, but in order to check whether a set of vectors is a tight frame, we do not need to check these equalities for any vector V. It is just enough to calculate some overlaps between the vectors from the frame and check whether they sum to a correct number. So that's why this condition here is in fact very easy to verify. Okay, now I would like to first some basic properties, some basic observations, how we can obtain morphophoric measurements from the existing ones. So the one procedure is that we've got a few morphophoric measurements with some possibly different parameters alpha, and then we can put together these measurements with some parameters T1 up to Tm, where this vector T1 to Tm is from the probability simplex. And this new measurement is again a morphophoric measurement, and this parameter alpha can be calculated from this vector T and from these parameters alpha j. We can also add a classical noise to a morphophoric measurement. And by a classical noise, I mean that we've got, we can obtain outcome J with the probability Qj, and we take a convex combination of these two measurements. So a morphophoric measurement with the classical noise. And it is again a morphophoric measurement, assuming that lambda is not 0, of course, because then we've got just the classical noise, and classical noise cannot be morphophoric because it's not informationally complete. Okay, so these are just some examples how to obtain the new morphophoric measurements from the existing ones. And now I would like to tell you something about the geometry of this image. of the state space by the morphophoric measurement pi. As we already know, this intrinsic geometry of this object is the same as the geometry of the state space. But here I would like to tell you something about the external geometry in relation to the probability simplex. So first, let me start with this theorem, this observation that if we take here, okay, maybe let me start with the notation here. So we take Vj to be the vectors corresponding to the effects in the space V. So we map the effects pi j back to the space V, and we take phi j to be the transferred by the measurement pi projections of these vectors pi j. So we know that this P0 Vj, in case of the morphophoric measurement, it is a tight frame in V0. And now we would like to show that this phi j are also a tight frame. But now it is in the linear space L, which is this space V0 mapped by the measurement P to the n-dimensional real space. And this observation is very simple, that if pi is morphophoric, then phi j is a tight frame in L, and the frame bound is alpha square. However, this is the condition which goes both ways. And however, in order for it to go back, we need to assume that pi is informationally complete. And that's why here in this theorem, we start with this assumption of informational completeness. And now, this is a simple remark here, that if we take the canonical basis in this n-dimensional space, so we take the vertices of the probability simplex, and we take the projection onto this space L, then these vectors phi j are the projections of this canonical basis up to this scalar factor alpha. And it is very easy observation. However, it is an interesting one, because well, from the Neymark theorem, we know that if we've got this tight frame in some space, then we know that there exists an orthonormal basis in the larger space, such that this tight frame is a orthogonal projection of this orthonormal basis in this larger space. So we know that there exists this orthonormal basis such that phi j can be defined as the projections of this basis. However, why it is in this case the canonical basis, this is some kind of magic here. Okay, and now a little bit more about this geometry with respect to this probability simplex. First, we define this affine space A. So it's the affine span of this mapped state space. And by delta, we denote the intersection of this affine space with the probability simplex. So here in this image, we've got delta. It's here is the intersection of A with the probability simplex delta 4 in this case. We also define C to be the point in this probability simplex which represent the probability distribution of the measurement outcomes for this maximally mixed state. And here we've got this. We can calculate this the coefficients of this state, and then we take Wj to be states. So we take these vectors that correspond to the effects Vj, and we normalize them so that they become states. And having these states, we define the basis distributions. So we calculate the probability distributions of these states obtained from the effects of the measurement. And these basis distributions will be denoted by Fj's, and we consider here this basis polytope D, which is a convex hull of these vectors Fj. So here is this yellow polytope. Here is this basis polytope, which is a convex hull of these basis distributions here. Okay, and now some a very important observation here, which is something new with respect to the geometry we already had in this state space in V. So we've got these two polytopes, the so-called primal polytope. So we so that was this delta here, and we've got the second polytope D, and somewhere in between we've got these possible probabilities. Now it is denoted by P. It was also called Gplex in the slides presented by Wojtek. And what we can say about these two polytopes. So here is the reminder what we mean by the dual set of A. And here we take the sphere which is centered at C. So that was this probability distribution corresponding to the maximally mixed state. And the radius S is set to be the square root of alpha times epsilon. And this self-duality
is the dual the same as the polar that was mentioned before? This notion of duality.
Dual is polar with the inversion.
Dual is polar with inversion.
Yes, I think.
With inversion with respect of this point C. So we have.
Got it. Okay, thank you. Thank you.
The polar is here. The inequality is different direction, and here we've got we don't have minus.
Yes.
Okay, so so this condition is kind of obvious because we started with this assumption that B is self-dual. So since pi is morphophoric, then also P has to be self-dual. So that's simple. But what is interesting here is that these two polytopes, D and delta, are also dual. And this is something really that again, it is easy to prove, but it is surprising, and in fact we do not understand it, in the sense that, okay, the proof is simple, and you see how it is done, and you see that it is easy and everything, but why it happens, why this geometry is it looks in that way, it's something that still puzzles us, and we haven't figured it out yet why it's the case. Okay, so to see why this condition is kind of weird, I would like to show you some examples. First example is the Pentagonal Space. So here we've got these vertices of the regular pentagon that is centered at 0. It's in the two-dimensional space, and we shift it to the third dimension, and we've got these vectors zj. Here the parameter A is chosen in such a way that this orthoisomorphism is the identity map, so that's just for the simplicity here. And in this case, the most natural choice of a morphophoric measurement is the pentagonal one, so like the same as the states in some sense. So we've got effects here, the same. Well, we take these extremal states and normalize them so that sum of pi j is E. And in this case, the simplest case, we obtain that all these sets D, delta, and P are the same. So it's just a regular pentagon. So it's nothing interesting here. However, we can also consider another morphophoric measurements. So in case of this pentagonal space, the minimal morphophoric measurement needs to consist of 3 effects, and one of these minimal measurements is given here. So we take 3 vectors such that they correspond to vertices of the equilateral triangle, and we take here our maximal possible. It's I wrote here maximal possible just because the formula for R is quite complicated, and it's not really important here. So we can calculate the basis distributions, and now because it has this measurement has 3 effects, so we map state space B into the two-dimensional simplex, so it is easy to draw. And here is our delta, which is actually the whole simplex delta 3. And here is the orange one is the basis polytope D, and the yellow pentagon here is just our pentagonal state space mapped by P from V to this simplex.
Sorry, is it the maximal pentagon, regular pentagon you can put inside a triangle, a regular triangle?
I'm not sure which one is maximal, this one or this one.
Or they are the same, concerning the size?
Because they are not the same.
Concerning the size, maybe they are the same.
I'm not sure. I don't remember, to be honest.
Okay, okay. Sorry, Anna, we should finish soon, in a few minutes.
Okay. Well, I'm just showing you the examples. So here is the same but rotated. And now I would like to show you something. Well, what happens if we add the classical noise? So I think I'm. So we can add classical noise, and I hope you can see it. And this simplex remains the same. The state space is, of course, of the same shape. However, it moves somewhere inside this simplex, but this basis polytope changes its shape. But
the yellow pentagon, can it also rotate a bit? Or it's only a shift of the pentagon?
If I remember correctly, not with this well, how no, in this case it also moves around. It can shrink in size, but because how this pentagon is orientated in this large simplex, it depends on the on this on this pi j used here. So it depends. So well, it could be this one or this one, and or some other one, but it is fixed. Okay, so this in some sense fixes the rotation of this pentagon. The lambda controls the size of this pentagon, and this qj controls the center of this pentagon. So that's the geometry here. But what's interesting here is that these two triangles, green and orange, are always dual. However, with respect to another ball. So this is something very interesting. Okay, I guess I ran out of time, so well, I can show you some other examples, like we can have ball and the minimal morphophoric measurement, which consists of n effects. So we obtain two simplices here that are dual. So this is again the no noise case, but we can also have other measurements here that are morphophoric. For example, a morphophoric measurement which is defined by the vertices of the hypercube, and then the this primal polytope delta is the cross polytope, and we can also add some, and we can also change this this scenario here. So we can take a measurement which is defined by the vertices of the cross polytope and obtain another image here, which in case of the if we add some noise, we obtain such a strange object like here. So this is also with adding some noise to the case when the morphophoric measurement is represented by the vertices of a cross polytope.
Thank you. So are you done, or would you like to conclude your talk?
I would like.
Yes, so maybe we
I
can.
think Wojtek would like to finish.
Good. So Wojciech, please go ahead.
Okay.
Oh, sorry. Maybe okay. Maybe let's ask questions to Anna later on. Yes. Let's have now conclusion.
Just short conclusions. Are they visible?
Yes. Urgleichung. Yes.
So in this approach, we try to extend the formalism of cuplexes and cubism first in two stages. First, replacing SIC-POVMs in quantum theory with morphophoric measurement in quantum theory. It was in our paper from last year. And now we go even further and we try to replace them, this quantum situation with some more general probability theory. But again, we would like to show that one can define morphophoric measurements also in this more general setting. In particular, we show that we can link probabilities of arbitrary measurement with some probabilities of some special measurement, which is in our case this morphophoric measurement. And we tried to understand the sources of different ingredients of qubits. For instance, this the fact that the state space lies somewhere between two balls is connected with the state space, with this property of self-duality of the state space. But on the other hand, the fact that it lies between two polytopes, as Anna showed us, is connected not with the state space, but it is connected with this morphophoricity of the measurement. So it is a kind of work in progress because it's not finished. But I think that we observed that many features of this, many geometric features of the cubist approach can be generalized to much more general case. So in the sense they are not quantum, because they can be present also in classical case or in some toy models. And one more comment. Anna told you that this theorem about this equivalent condition about tight frames and morphophoricity is ours. It was not true. It is hers. So I didn't take part in formulating this theorem. So I would like to be correct here.
Thank you very much. So thank you both for the presentation, joint presentation, and thank you. And let us start the discussion. So who of you would like to ask a question to Anna or to Wojciech? Please go ahead.
I have it's a small question over the pentagonal space. So since the spectrality in case of pentagonal space is coming out to be √5, so can you conclude from here that because it's not some natural number, so can you conclude from here that pentagonal space does not exist in nature, like quantum space and classical space?
Sorry, I have had some problems with there was some noise, so I don't understand everything.
Sure. Since the spectrality of pentagonal space is not coming out to be some natural number, it's coming out to be √5. So can we conclude from there that pentagonal space does not exist in nature, or it's yeah.
Sorry, I have a large noise, and
I think I've heard that the question was whether this the fact that this parameter Chi over epsilon is square root of 5 in the case of pentagonal space.
Oh,
Does it mean that the pentagonal state space cannot occur in nature? Right? That was the question.
Yeah, absolutely. Thank you.
Okay. But I don't know how to answer.
I think that that only the quantum theory is the only theory which can appear in nature because the world is quantum. So all other theories are in a sense wrong. And as far as we know, so it's a difficult answer. But I understand that the question is there any difference between situation when this parameter is natural and what is the meaning of this parameter where it is not natural? It is a kind of informational capacity in the spectral theories. And what does it mean if the theory is not spectral? What is the meaning of this? Is there any meaning of connected with information theory? Well, I don't know. I would like to know. I thought about this problem few, maybe not even minutes, but hours, but I don't know the answer. But it is very, very interesting thing. Is because we noticed that this parameter appear in many formulas here. So in a sense, it is crucial, which is not, maybe it is not visible in a concrete theory, and it is, I think, a good an interesting feature of general approach that if you have a quantum theory, then it is not visible because this parameter is just the dimension of complex space. So if you have a classical theory, again, it's a natural dimension of number of vertices of the simplex. So it is not visible. So in a sense, it's easier to understand what this parameter is, and to I think that it is one important point here, that it is a reasonable task to analyze the more general theory, just to understand the quantum situation or classical situation, just because these parameters are visible and they weren't there. So, but of course, it means that there are also some questions like what does it mean if it is not natural? And so the answer is, I would like to know, but I don't know. We don't know.
Okay, are there further questions from the audience?
May I try?
Yes.
I have to exhibit a basic confusion. So this goes to Wojciech's talk. If I consider the quantum mechanical case, I can take a complete set of MUBs and create from it a morphophoric map. But it doesn't preserve the dimensionality. I find that the quantum state space gets mapped into a subspace of the simplex. But the elements of a complete set of MUBs don't satisfy the equiangular condition. So I'm confused on one of the theorems you exhibited to us.
I think there's a misunderstanding in this because the morphophoricity, the theorem says that the morphophoricity maps orthogonal states, orthogonal frames into equiangular lines. So it has nothing to do with the effects that consist
Oh,
morphologic.
okay. Yes. So
So
it's,
that is double meaning of the word equiangular, and in this. So
okay.
it was confusing. I
Okay.
must say.
Okay. So this also explains my earlier confusion. So I think I have it now. Okay. So
Okay.
now a fresh question. Might it
Yes.
be, so this is a hypothetical, of all GPTs, quantum theory is the only one that has a morphophoric map that, so this would demand SIC existence, but might it be that of all GPTs, quantum theory is the only one for which there's a morphophoric map that takes the uses the full dimension of the simplex? Or do you have a counterexample?
Definitely in quantum case, the answer is, if it is full dimensional, it must be SIC-POVMs, of course.
Yes.
But what about some other GPTs, Anya?
but you can always, well, if I understand the question correctly, you can always take minimal morphophoric measurement with the minimal number of effects. And
No, I don't think you can. Not, for instance, in the real vector space case, you would need, I believe, well, I don't know. But okay, so I apologize, Anna. Please continue.
But I think that in classical world it is possible, of course. But
if I can show you again these examples here. I'm not sure whether I understand it correctly, but here is the, for example, we've got the state space, which is just a ball. And here, of course, this picture is in two-dimensional case, but it is easily, it can be easily generalized to any dimension.
I have to stop sharing. Sorry.
No, I think.
And your picture is visible now, I think.
Okay.
Yes,
so,
it is. It's fine.
So we've got this. This ball is n-1 dimensional, and we take the measurement that is defined as here. So we take the vertices of regular n-1 dimensional simplex inscribed in B, and then we obtain here as this primal polytope, we obtain this full-dimensional simplex. So I'm not sure whether it answers your question.
It is a counterexample, I think.
So the state space, so all I'm asking is, and it sounds like you do have a counterexample. My question is simply, can we find a morphophoric map such that the dimensionality of the state space and the dimensionality inscribed in the simplex is the same? And I think you're saying yes, you have an example.
Yes, I think.
And it is not quantum.
And I believe it's always possible, actually.
You believe it's
maybe
always
not always it will be in this this nice picture, but I mean, even in the quantum case, when we do not know whether the SIC-POVMs exist, but we can take some noisy measurements, and if we shrink it in size, this set, we can always fit into the state space. Yes.
Right.
So well, it won't be so easy.
Okay, so
Right.
then a refinement of the question would be, could it be that the quantum case is the only one that preserves dimensionality with a measurement that consists of extreme points? So not your noisy ones.
What about classical case? In classical case, you can have a trivial measurement, just identity map from simplex to itself.
Yeah, but that's an example of a noisy measurement. It reveals no information.
So
Yeah, I mean, clearly I'm looking, I'd like to find out what distinguishes quantum theory from all the other GPTs.
yes,
And I've always hoped that a large component of the distinction will be the existence of SIC-POVMs. But now you've changed the language to questions about morphophoricity. And so this is why I'm pushing in wondering what makes a morphophoric map with SIC-POVMs special in all GPTs.
yes, I understand this line of reasoning, and definitely there are some possibilities here, but also in quantum case, you can have many others morphophoric measurements, but they are not full dimensional. So this first part of the question is, I think, important. Well, it is. I think
so
that
look,
it's a question to how to seek the equivalent condition for SICs and quantum.
yeah, I have now some simple idea, because we are a bit out of time. So I suggest to finish the official seminar, and then who would like to discuss, we can still continue sitting here. So let me now officially thank Anna and Wojciech for a very nice talk, and wishing them even nicer results in second paper. Thank you. And now a short announcement.